Sir, Dr. Arivanandhan sir, good morning sir.
Good morning sir.
Good morning sir. Principal வந்துட்டு இருக்காங்க சார்.
Okay, no
problem. வந்துருவாரு. இப்போதைக்கு
முருகானந்தம் சவுண்ட் வரல.
பிரின்சிபல் சார்
Sir, good morning, sir.
Good morning.
Good morning, sir. Sir, start பண்ணிடுறேன் sir.
Yes, sir.
Great things are not done by huge impulse, but by the series of nano sparks brought together. A very pleasant morning, everyone gathered. A small cheer and a great welcome makes a valuable webinar. The person who organized something exceptional, Dr. S. Pari, Organizing Secretary and Head of the Department Physics, National College, to deliver the words of welcome.
Good morning, everybody. Distinguished Chief Guest, Dr. M. Arivanandhan, respected Secretary Sri K. Raghunathan, beloved Principal Dr. R. Sundararaman, I deem it a privilege and honor and very happy to welcome you all for this memorable national webinar of our veteran physics department. At the outset, I wish to state that we are all inspired and very happy by the presence of today's chief guest, Dr. M. Arivanandhan. Thank you very much, Professor, for your kind acceptance to give a webinar amidst your busy schedule. About the field of thermodynamics is an important technology to convert the heat into electric energy. By developing the technology, one can control the energy and environmental problems. Dr. Arivanandhan is working on thermodynamics for the period of past 10 years and developed different methods and fields to prepare highly efficient thermoelectric materials. I convey my sincere thanks to our beloved principal, Dr. R. Sundararaman, for his presidential address. I welcome you, sir.
Thank you.
I welcome all professors, colleagues, research scholars, staff from various departments, and also from other colleges, public, and my dear young dynamic students. In this occasion, I extend hearty thanks to our secretary and beloved principal. Finally, once again, I welcome one and all participants to this great webinar. Thank you.
Thank you, sir, for your pleasant welcoming. If your actions inspire others to dream more, do more, learn more, and become more, you are a leader. Now, I request such a leader, Dr. S. Sundararaman, Principal, National College, to address the meeting.
Most esteemed speaker, Dr. Arivanandhan, Associate Professor, Center for Nanoscience and Technology, Anna University, Chennai. Dr. Pari from the Department of Physics. Dr. S. Muruganandam, Convener. Dear colleagues of the Department of Physics and other departments, my dear students, good morning to every one of you. I am happy to preside over this national webinar basically for two reasons. Number one, the speaker, and number two, the topic. Dr. Muruganandam, Dr. Arivanandhan is a famous expert on the subject from the prestigious Anna University. The topic nanostructured oxide materials is of great importance. Nanotechnology enables tailoring of structures of materials at extremely small scales. The materials can be made more lighter, more durable, and so on. Many new materials with unique characteristics have been developed through research in nanotechnology. To put it simply, nanotechnology helps us to get fantastic products with wonderful features. This webinar focuses on nanostructured materials for thermoelectric applications. The field of thermoelectrics has been recognized as a potentially transformative power generation technology. The field is now growing steadily due to its ability to convert heat directly into electricity and to develop cost-effective, pollution-free forms of energy conversion. Of various types of thermoelectric materials, nanostructured materials have shown the most promise for commercial use because of their extraordinary thermoelectric performance. Nanostructured materials are functionally superior. Dr. Arivanandhan will highlight the application of the materials in thermoelectrical. I am sure his brilliant exposition will help you to understand the use of such materials. I thank our learned guest for accepting our invitation. I take this opportunity to convey my best wishes for a happy and prosperous New Year. Once again, I wish this webinar a grand success. Thank you very much.
Thank you, sir.
Thank you, sir. To be inspired is great, but to be an inspiration is an honor. I call on Dr. S. Muruganandam, convener, to introduce our honorable chief guest.
Very good morning to all. First of all, I would like to thank our secretary, principal, and head of the department for constant encouragement and support for conducting this type of webinar. It is a great privilege and honor bestowed upon me to introduce today's resource person. Associate Professor, Center for Science and Technology, Nanostructured, Chennai. He completed his undergraduate in physics at University of Madras, Chennai. He did his post-graduation at Alabama University. He has 20 years of experience in teaching and 20 years of experience in research. He has published more than 150 international journals. He reviewed more than 60 papers in journals like Elsewhere, Springer, and also editor in Journal of Crystal Growth. He authored in Japan patent in publications. Research project to the tune of core from grant in aid for scientific research B from Ministry of Education and Culture, Sports, Science and Technology, Japan, and lakhs from DST in India. He is a member of several academic professional bodies in the field of material science and engineering. He is a several awards and recognitions. ISPA Dr. S. Gunasegaran Award by Indian Spectrophysics Association, Young Scientist Award 2018 in Physical Science by Academic of Science, Chennai. Young Achiever Award, Elevenil Science Association, Chennai. Very interesting, he is an eminent editorial board member of the journal Crystal Structure, Theory and Applications. With this short introduction, I would like to invite our today's resource person, Dr. M. Arivanandhan, to deliver his lecture. Thank you all.
1 second, please.
Thank you, sir. Now, I request our chief guest, Dr. S. Arivanandhan, an idol of knowledge and experience, to please come on to the screen and fulfill our knowledge with your words.
Thank you, sir. Yes, sir. Welcome, sir.
Thank you, Dr. Muruganandhan, for your very nice introduction. Respected principal of this college, Professor Sundar Raman, and head of the department, Dr. S. Pari, and the convener of this program, Dr. S. Muruganandam, and all other department colleagues and the participants. Very good morning to all of you. Audio is clear, no? Sir, how is my audio? Is it clear? Please, one of you unmute your mic and tell me. Then I'll continue. Is it clear? Hello?
Yes, sir. Yes, sir. Clear, sir.
Audio is clear.
Audible. Audible.
Okay, fine. So I'd like to thank all the team members for inviting me to give a lecture on thermoelectrics on this great occasion. And we are under lockdown and we are working from home with the safe and safety precautions. So this kind of webinar will be quite useful for the youngsters to refresh their knowledge in advanced science and technology. Okay, so in that aspect, Professor Pari and his team are organizing a series of webinars like this. And today I'm going to talk about the oxide thermoelectric materials. So this is one of the recent hot topic of research. People are working on different kind of oxide material. So I'm going to give some highlights on the recent research in oxide thermoelectric material and the importance of this oxide thermoelectric material for energy conversions. Okay, so let me share the slides first and then we'll go into the content. Yeah, I hope you can see my slides, right? Can you see the slides? Hello. Yep.
Yes, sir.
Okay. So please mute your mic and then I'll continue my talk. Okay. So this is the topic, the nanostructured thermoelectric materials. As the principal and the head of the department, Dr. S. Pari, pointed out, the thermoelectric is a technology to convert the thermal energy into electrical energy. Okay, so in that aspect, the thermoelectric research is dominating the recent literature because the main issues what we are facing current recent days, as well as of course we are going to face in the future, is that the energy demand as well as the environmental problems. Okay, so these two are the main issues. One has to concentrate on that to develop some sustainable future. So for that we have to decrease the dependency of conventional fossil fuel, and as well as you have to control the environmental pollutions. Okay, as you know, the industrialization and the automobiles are increasing day by day, right? And these kind of automobiles and industrializations, they are emitting a lot of heat energy into the environment. Okay, and that will give some subsequent effect, and which will leads to the global warming. And we are one of the leading CO2 emitters in the world. Okay, so this CO2 is mainly contains in the exhaust of automobiles as well as the industrial exhaust. Okay, so by effectively recycle these industrial waste as well as industrial waste heat as well as the automobile exhaust, then somehow you can control the CO2 emission, and that will leads to green environment. Okay, and in which way you can recycle. So by using this technology, the thermoelectric technology, you can recycle the waste heat to convert into the electricity. So by establishing such kind of technology, you have the opportunity to control both the environmental issues as well as the energy demand problems. Okay, so in that aspect, this technology is playing a role in for the present as well as future generation. This is the schematic of a thermoelectric cell. It consists of two material. One is written as P and another one is written as N. These are all nothing but the P-type semiconductor and N-type semiconductor. And when you connect these two semiconductor at one end, and when you keep the another end as open, and when the junction exposed to the thermal energy, then the charge carrier in the respective semiconductor will diffuse from hot end to the cold end. Right? That will lead to generate the potential, and that can be used for your practical applications. Okay, so in that aspect, this thermoelectric technology can convert the waste heat into electrical energy. Okay, and that waste heat can be from different sources. That may be from this kind of a forging, or some kind of in the power plant, or some kind of incinerators, or it may be some kind of exhaust of the automobile, like that. So wherever the heat and energy are coming out, where if you place this kind of thermoelectric cells, and that can convert the reasonable amount of heat energy into the electric energy. In that way, you can able to fulfill the energy demand and control the environmental pollutions. So what is the current strategy of this thermoelectric technology? Okay, so the current scenario of this thermoelectric technology is almost half of the way. A part of the technology is commercially available, and based on few kind of material, and most of the materials are under R&D. Okay, and what are the commercial potential for this kind of material? So these are all already the commercialized technology, and that is called the catalytic converter. The automobile people, they used to call it as a catalytic converter. So this catalytic converter is playing a very vital role in automobile industries, especially in the kind of luxurious cars like Audi, Benz, like that. Okay, so what is the role of this catalytic converter? Why the people are using this catalytic converter is here, you can see. So before that, let us see about how you can you can make a thermoelectric module. Okay, so module is nothing but previously what I have shown is a thermoelectric cell, and if you connect a series of cell together, then you can fabricate the module. Okay, to have, if you have a module, then the large area can be used to expose the waste heat, and then you can scale up the power conversion. And that can be done by connecting the p-type and n-type thermoelectric legs like this. Okay, and this is a schematic of this thermoelectric module. And once if you have this kind of series of thermoelectric cells, then the area of exposure of thermal energy will be more, and then the thermal power can be increased. And by using that technology, you can fabricate this kind of TEG, that means catalytic thermoelectric generator based catalytic converter. Okay, so the automobile people, they used to place this kind of thermoelectric generator in between the exhaust and the engine of the automobile. Okay, and when the exhaust which are coming out from the engine can go through this TEG, the thermoelectric generator, and during this kind of passage, the part of the waste heat, the heat energy, is converted into the electricity, and this heat energy can be used for interior purpose of the automobiles, like the seat warmer, interior purpose of the automobile. And the exhaust emission through this TEG contains less pollutant. So that's what the people have already established this technology, and the people, they used to call it as a hybrid technology, hybrid automobiles. So in this kind of hybrid automobiles, the rate of pollutant is very less compared to the automobile without the catalytic converter. And because of that, the people have developed different kind of TEG and different dimensions of TEG, and they used to place in different kind of automobile to effectively convert this kind of heat energy into the electricity. But the idea of this technology is that you have to have some temperature gradient. So your hot end should be more hotter and hotter, and your cold end should be more colder and colder. So if you have such kind of the temperature difference between the hot end and cold end, then you have the effective energy conversion process. So to have that steep temperature gradient between this hot junction and the open end, you can do these kind of modifications, like you can put some kind of incinerators at one end, and you can put some kind of effective coolant at the other end. Then you can have the drastic change in temperature between the hot end and cold end. And once if you have that kind of steep temperature gradient, then the thermal power can be scaled up. So that is the idea. By using that, the people are working on different aspects, how one can modify the cell structure, and how one can modify the heat sources, and how one can modify the cooling system to effectively generate the thermal gradient, so that we can effectively harvest the the energy. Okay, so in that aspect, the people are working in different kind of materials. And these are all some of the thermoelectric cells which are available in the market. Even in the online market like Flipkart or Amazon, you can buy this kind of thermoelectric uh, module. And this kind of model, maybe as a teacher, as a college professor, you can use it for a demonstration purpose. Say for example, you can show it to our student, and by giving some thermal energy at the opposite end, and if you connect this wire, black wire and red wire, to the either a kind of DC motor, then by giving some by lightening the hot end, you can have some kind of energy, electric energy. And by using that electric energy, even a DC fan can run. Okay, so that's a kind of demonstration how the thermal energy can be converted into the electrical energy. But it has a lot of scope to scale up the technology as well as to improve the conversion efficiency. So how? So these are all some of the innovative approach that people are following all over the world to improve the thermoelectric conversion efficiency. So the first aspect is that the optical concentrator. This is one of the recent innovative approach that instead of thermal energy which are coming out from different industrial sources or automobile, you can create the thermal energy from the solar radiation by properly establishing some optical concentrator. Okay, so these optical concentrator will converge the incoming solar radiation to the hot end of the thermoelectric cell. And by converging, the reasonable amount of thermal energy can be generated at the junction of thermoelectric cell. And on the other hand, you can establish some kind of effective cooling at the cold side. So by creating this kind of the optical concentrator and effective cooler, you can have the steep temperature gradient, and that will lead to generate the electricity. So not only the optical concentrator, you can put some kind of reflectors like parabolic reflectors. So these kind of the parabolic reflector will so incoming solar radiation can be incident on the parabolic reflector, and it can be reflected back to the hot end of the thermoelectric generator. And by doing this kind of parabolic reflection, one can have high temperature at the junction. And by establishing some cooling arrangement at the opposite end, you can have the strong temperature gradient. And once if you have the temperature gradient, and that will lead to conversion of electric energy. So these are all the kind of the innovative approach for increasing the conversion efficiency of a thermoelectric cell. And nowadays, the floating solar cells are becoming very famous. So they they used to float the solar panel on the sea surface. Then by absorbing a lot of solar energy. So similarly, you can establish the solar thermoelectricity based on this. One is that in this kind of floating solar thermoelectric cells, you can have the effective cooling, because the cooling cold end is having direct contact with the sea surface. Okay, so that you need not have the separate cooler for the cold end, and the seawater can effectively cool the cold end. And on the top end, hot end, you can put some kind of selective absorber, like this kind of some kind of effective absorber, like the black body coating. Then it can harvest more amount of solar radiation. So by absorbing more amount of solar radiation and by effectively cooling at the opposite end, you can have the steep temperature gradient, and that will lead to effectively convert the electric energy, thermal energy, into the electrical energy. Okay, so this is a solar thermoelectric technology. Like that, you can use the thermoelectric technology to convert the thermicity. and the thermal energy may be from different form or from different source. It may be from automobile exhaust, or it may be from outlet of the incinerators, or it may be from the outcome of the thermal power plant, like that. But by using the technology, you can convert that kind of thermal energy into the electrical energy. But the application of this thermoelectric technology is not only limited to this energy conversion process. As well as you can use this kind of technology to have some kind of cooling effect. Thermoelectric coolers, thermoelectric Peltier coolers. As well as you can use this kind of technology as a IR sensor. Because this thermally accelerated electrons can diffuse, or thermally accelerated charge carrier can diffuse from the hot end to the cold end, and you'll have the thermo power in the power generation mode. Okay. At the same time, if you give some electric potential at the cold end, and based on this current flow in the closed loop, you can have a Peltier cooling at the junction. So this is based on the Peltier effect. So both version of the technology is possible. You can have the electricity, as well as you can, by giving the electricity, you can have the thermal heating as well as thermal dissipation. So that you can use this kind of thermoelectric Peltier module as a heater and cooler for the sensing the temperature as well as for heating the system. And here you can see it's a kind of arrays of thermoelectric module, and wherever the IR radiation incident on the module, then the thermo EMF may change. And by detecting the change in the thermo EMF, one can sense the presence of IR radiation on the surface. So in that aspect, you can use it as a IR sensor. Okay, so all are mainly based on the basic fundamental physical parameters of the basic constituents of the device. So the basic constituents of the devices are nothing but the semiconductor material. Let me tell you why semiconductor material in the coming slide. But before that, let us see what are the the important parameter one has to concentrate to improve their performance. So these are all the parameters listed here. One is the first of all the heat energy, how much energy is incident and how long exposed to the thermoelectric cell, and what is the chemical potential of the material, and then the electron charge and density of states, and especially these three parameters. One is the thermal conductivity, and another one is the electrical conductivity, and another one is the Seebeck coefficient. So these three are the important parameter one has to concentrate to effectively improve the overall performance of the thermoelectric cells. Okay, so the performance of a thermoelectric cell can be determined based on the figure of merit. The figure of merit is here. It's nothing but it's the ratio between the power factor and thermal conductivity. Okay, and the power factor is nothing but the product of square of Seebeck coefficient and electrical conductivity. Okay, and from this relation you can understand the figure of merit is directly proportional to the power factor and inversely proportional to the thermal conductivity. So if you want to improve the figure of merit, you have to do this kind of tuning. Either you have to increase the power factor or you have to decrease the thermal conductivity. But the problem is here. So how one can, whether is it possible to improve the power factor and decrease the thermal conductivity? It's quite difficult, because you can see the thermal conductivity contains two components. One is the electronic part of thermal conductivity, and another one is the lattice part of thermal conductivity. Right? So according to the Weidmann-Franz law, the electronic part of thermal conductivity is directly proportional to the electrical conductivity. Right? So it's quite difficult to independently control the electron transport and thermal conductivity. So if you control the electrical conductivity, then thermal conductivity also will be controlled. But if you want to increase electrical conductivity, then thermal conductivity also will be increased. But the thing is that the Feynman-Franz law is valid only for a high electron density material, like metallic material. Whereas if you choose a low carrier density material, like semiconductor material, then the electronic part of thermoconductivity is quite low compared to the lattice part of thermoconductivity. So by properly engineering the semiconductor with the appropriate carrier density, you can prepare a material with low carrier concentration. Then there you can have the dominant lattice thermal conductivity compared to the electronic part of thermal conductivity. So, and another important information is that the lattice part of thermal conductivity is no longer related to the electrical conductivity. So that is why the people are working on semiconductor-based thermoelectric material. And once if you have such kind of a semiconductor-based thermoelectric material, you can have the high lattice part of thermal conductivity. By properly controlling this lattice part of thermal conductivity, you can enhance the figure of merit. And by properly doing the doping engineering, you can enhance the power factor of the semiconductor-based thermoelectric material. So this is the kind of strategy that people are following to improve the performance. But what is the current scenario of this thermoelectric technology is here. You can see the thermoelectric efficiency is not up to the level. The thermoelectric efficiency is not up to the range of silicon-based photovoltaic, because the silicon-based photovoltaic is a kind of well-matured technology, where you can have the conversion efficiency in the range of 15 to 20%, based on the kind of silicon wafer used for the solar cell. And also you can have the lifetime of about 15 to 20 years. But the commercialization as well as the performance of thermoelectric technology is not up to the level. Then if you want to improve the performance up to such kind of technology, you have to concentrate on the material property. And here you can see this is the conversion efficiency of a thermoelectric module. And this conversion efficiency relation is a function of temperature gradient as well as the figure of merit. Okay, and based on this relation, one can calculate the conversion efficiency as a function of two factors. One is the hot end temperature, and another one is the figure of merit. Right. So here the data are here, the theoretically calculated data. Look at the data. That means this my conversion efficiency is increasing as a function of temperature, right? As well as it is increasing as a function of figure of merit. So from this kind of theoretical data, you can understand that you can increase the conversion efficiency by two aspects. One is that if you have your ZT of about 1, then you can realize the efficiency. The dotted black line shows the efficiency of 20%, which is comparable with the polycrystalline silicon-based solar cell. So if you want to realize that much of efficiency, you have to increase the hot end temperature up to 1200 if your ZT is about 1. On the other hand, if your ZT is very high, even you can realize the same efficiency at half of the temperature of about 600 Kelvin if the ZT is about 3. Okay, so either by increasing the figure of merit or by increasing the hot end temperature, you can increase the conversion efficiency of this thermoelectric cells. So how one can increase the efficiency? So obviously, to increase the efficiency, you have to increase the figure of merit, as we have seen from the previous slide, right? So if you want to increase the figure of merit, here is the strategy. So this is nothing but it's a schematic of nanostructured bulk material. So if you have this kind of nanostructured bulk material with all these kind of grain structures and some kind of defects and some kind of grain boundaries and some kind of alloying and some kind of lattice misfit, then this kind of nanostructured bulk material with reasonable amount of defects are quite beneficial for improving the thermoelectric performance. So how the defects are beneficial, let us see here. So as I said before, the electronic part of thermal conductivity is quite, directly proportional to the electrical conductivity according to the Weidmann-Franz law. Whereas in semiconductor-based material, the lattice part of thermal conductivity is dominant, right? So how the lattice part of thermal conductivity is changing based on the material? Here you can see the relation. So the lattice part of thermal conductivity is a function of these three parameter. One is the specific heat capacity, and phonon velocity, and phonon mean free path. Okay, so you can play with this phonon mean free path by creating these kind of defects. So these defects are acting as a phonon scattering centers. So these defects may effectively scatter the phonon, and by effectively scattering the phonon, one can control the phonon mean free path. So if you control the phonon mean free path, you can control the lattice part of thermal conductivity. So by controlling the lattice part of thermal conductivity, you can have the high figure of merit. And by increasing the high figure of merit, you can have the high conversion efficiency. So that is the idea. The people are working on nanostructured material by creating a lot of defects like these, kind of inclusions, and some kind of inclusions at the grain, as well as at the grain boundaries, as well as some kind of the alloying and some kind of doping. So all these things are quite useful for creating some kind of phonon scattering center, and that will effectively control the lattice part of thermal conductivity, and that leads to enhance the figure of merit. Okay, so in that aspect, and we are also working on the doing some kind of carrier engineering for enhancing the power factor, as well as by doing some kind of grain structure engineering, one can control the lattice part of thermal conductivity, and by doing that way, we can enhance the thermoelectric performance. So these are all the fundamental relations, the thermoelectric parameter, how they are changing with respect to the carrier concentration of a material. So the carrier concentration, you can classify the material based on the carrier concentrations like insulator, semiconductor, and metal. And for insulator, you have the very poor carrier density, so that the electrical conductivity is very low, as well as the Seebeck coefficient is quite high. Whereas in the metallic material, the carrier densities are more, so the conductivities are more, electrical conductivity. And you can see the electronic part of thermal conductivity also follow the same trend of the electrical conductivity according to the Weidmann-Franz law, right? So then this is the optimum range of concentration, dopant concentration in the semiconductor. So in this kind of doping concentration is quite promising for realizing the high performance. Okay, and these are all the novel approaches that people are following to improve the performance of the thermoelectric material. Okay, so the first aspect is that reducing the thermal conductivity without affecting the electrical conductivity. That is the first idea. So for that, you have to introduce some kind of nano inclusions or defects as a phonon scattering centers, and that will leads to control the thermal conductivity without affecting the electrical conductivity. Okay, and nanostructuring the material. This is another important approach. By doing this kind of nanostructuring, you can play with the DOS, density of states of the material, and that will lead to independently control the electrical conductivity and Seebeck coefficient. And also, by creating this kind of nanostructured material, you can create a lot of interfaces with the grain boundaries. So these kind of interfaces will have some kind of selectivity of carrier transport, and that will lead to scatter the phonon as well, and that will lead to reduce the thermal conductivity. And the energy filtering effect, that is another beneficial aspects of nanostructuring the material by create with a lot of interfaces. So these kind of grain boundary will act as some kind of potential barrier for the carrier. So based on the energy of the carrier, the high energy carrier may go through the potential barrier, whereas the low energy carrier may not. So like that, some kind of selective transport can be realized, and that will leads to improve the thermoelectric performance of the material. So the ultimate aim of the thermoelectric researchers is to design a material like phonon glass electron crystal. So what do you mean by phonon glass electron crystal? This is nothing but you have to have a material which should have phonon transport as like in the glass, and electron transport as like in the crystal. Then it will have the high thermoelectric performance. Okay, so what is the exact the impact of nanostructuring on thermoelectric performance. Okay, and look at the DOS variation. See, this is the DOS density of states of 3D material, that means bulk material. The density of states is quite continuous, whereas when you have some kind of directional confinement in the bulk material, say for example this is the two-dimensional material with one-dimensional confinement, so that means this is the confinement direction, and these are all in this direction. The electrons are freely move with this wave vector along x-axis and y-axis, whereas this is the confined direction with the quantum well thickness of about d. Okay, and once if you have this kind of energy distribution, then the density of states will change like this. So the density of change is increased by the confinement. Okay, and once if you have this kind of change in the density of state, and that will lead to change the effective mass, since the effective mass is a function of density of states. Okay, so once if you increase the effective mass through the confinement, then the S can be improved, because then S is directly proportional to the effective mass. The S is nothing but the Seebeck coefficient. So by doing this way, you can independently control the Seebeck coefficient and electrical conductivity. And this is some of the the theoretically calculated data for ZT for bismuth telluride in two different confinement directions. So in a certain direction, the ZT is quite high, as well as the power factor. The power factor is also quite enhanced by tuning the thickness of the quantum well. If you have very narrow range of quantum well, you can increase the power factor. So like that, these are all the beneficial aspects of nanostructuring the material for improving the thermoelectric performance. And how the phonon glass electron crystals looks like. So the most of the layered materials, like the high TC superconductor material, superconductor like materials, like the high TC superconductor materials are like a highly complicated structure with multiple components. And once if you have such kind of the multiple components with the complexity in the structure, and that will lead to increase the randomness in the system, and that will have some kind of effective phonon scattering, as well as so due to its high electrical conductivity, it should have some kind of electron transport. So once if you have that kind of high TC based structures, then you can have the reasonable phonon scattering as well as the smooth electron transport. Okay, and on the other hand, these kind of layered structures. So these kind of layered structures are quite promising for realizing this phonon glass electron crystal system. Okay, so the people are working on different kind of the layered materials and highly complex crystal structured materials, like high entropy alloys and topological insulators. So these are all the the recent hot material for realizing the high thermoelectric performance. Okay, and these are all some of the reported results on nanostructured material, how the nanostructuring is helping for improving the performance. Okay, and look at the data. So this is the data for bismuth, lead telluride and lead selenium telluride based material, and the power factor is enhanced for nano compared to the bulk material. On the other hand, the thermal conductivity is drastically decreased compared to the bulk material, right? And due to this kind of drastic variation in the power factor and thermal conductivity, the figure of merit has been enhanced. Okay, so similarly for the bismuth telluride and antimony telluride nanostructures, it shows the high thermoelectric performance compared to the bulk material. Okay, so these are all some of the examples from the literature. And these are all some of the material which are available in the literature, and most of them are under R&D, and some of them are commercially available, like bismuth telluride and silicon germanium. And silicon germanium is the only material which can withstand more than 1000 Kelvin, especially the semiconductor-based material. And the rest of the materials are quite stable at the temperature range of below 1000 Kelvin. Okay. And that is the reason the people have moved towards the oxide thermoelectric material. So the why the oxide means, here you can see the comparison. This is the oxygen-free thermoelectric material. Most of them are semiconductor-based thermoelectric materials. And as I said before, only the silicon germanium is the only material which can withstand more than Kelvin, right? Whereas here you can see the oxide material. Most of the oxide materials are quite active even after 1000 Kelvin. right? And the performance can be enhanced by properly engineering the material. But the main important difference is that the figure of merit. The figure of merit is quite high for the semiconductor based material, where even up to 2, nowadays more than 2.5 they have realized. And for the oxide based thermoelectric material, for most of the thermoelectric material, the figure of merit is less than 1, right? So this is the scenario why the people are working on oxide material. So although they are thermally stable, the performance is not up to the level. But whereas this semiconductor material, it's quite difficult to process the material. You need to have some kind of special environment, dust-free environment, and the dust-free conditions to process the material as well as to fabricate the device structure. Whereas this kind of oxide material is quite easy to process, and you can scale up the technology, as well as these kind of materials are quite stable against the atmosphere. So like that, due to that kind of beneficial aspects, the people are working on this oxide-based thermoelectrics to improve their performance. So we are also working on variety of oxide thermoelectric material. Just I'll quickly go through our results, and if you have any clarifications, you can ask me, no problem. Okay, so this is the bismuth zinc bismuth substituted zinc cobalt oxide. So the zinc cobalt oxide is one of the oxide based semiconductor, and it's quite rarely studied thermoelectric material, and we have chosen this zinc cobalt oxide, and systematically varied the bismuth substitution content at the cobalt site by properly optimizing the precursor concentrations. And this is the protocol which we used for synthesizing the material. And once if you have the synthesized powder, then we used to make it as a pellet, and we used to study the thermoelectric characteristics. Okay. So these are all the nanostructured material based pellets. So they used to make the pellet like different shapes, circular shape pellet, and thermoelectric legs. So if you have thermoelectric legs like this with optimized properties, then you can go for devices with the combination of p-type and n-type thermoelectric legs. Okay, so these are all although it looks like a bulk, when you look at the micro level or nano level, contains a lot of nanostructured grains in the material. Okay. Then the sample has been subjected to the X-ray diffraction analysis, and the structural patterns confirms the mixed phases of the zinc cobalt oxide. Sorry, up to the 10%, it's a pure phase, and when the bismuth content increased beyond 10%, the secondary phase has been obtained, and which shows that up to there's a 10%, the bismuth has been effectively substituted at the cobalt site, with showing the alloying effect of the waste system. And then due to the exceeding of a solid solubility limit, some secondary phase has been obtained. Okay, and all the structural parameters has been confirmed. And these are the morphological features of the sample, and the morphology has been systematically changed from the spherical to the sheet-like structure when the bismuth content increased in the system. Okay. And this is the morphology of the pelletized nanostructure. So that means even after pelletization and after sintering at high temperature, how the morphology changes. Okay, and the morphology has been retained even after the sintering at high temperature at the same particle and sheet-like structure. And this is the EDX analysis of the sample. And look at the sample. The EDX mapping shows that the each and every basic constituent elements are homogeneously distributed. Hello. Yes. Madam, now talk. Okay, so look at the mapping images. The elements are homogeneously distributed, and except this bright spot. Okay, and in this bright spot, the bismuth is quite rich, in addition with a reasonable amount of oxygen. Okay, so which confirms the presence of bismuth oxide in the zinc cobalt oxide phase. So during the sintering process, the secondary phase may precipitated as a on the surface, and that was recorded on the EDX mapping. So which further confirms the presence of secondary phase as observed in the X-ray diffraction analysis. And then the sample has been subjected for the electrical characteristics, and this is the the carrier concentration, which is measured by using the Hall effect system, and the carrier concentration has been increased with respect to the bismuth content up to 10%, and then slightly decreased at the high bismuth content. That's mainly due to the formation of the secondary phase. Okay, and the electrical resistivity and Seebeck coefficient of the sample has been measured. And look at the electrical resistivity. The electrical resistivity of all sample has been decreased, which shows the semiconductor behavior of the sample. And with respect to the bismuth content, the electrical resistivity has been decreased up to 10% and slightly increased due to the secondary phase formations. Okay, and the Seebeck coefficient also systematically varied with respect to the bismuth content, and that shows the relation between the electrical resistivity and Seebeck coefficient in the system. And from the measured electrical resistivity and Seebeck coefficient, the power factor has been calculated, and the power factor is quite high for the bismuth substituted sample compared to the bismuth free sample. And the best sample has been chosen to measure the thermal conductivity, and the thermal conductivity of a bismuth substituted sample is quite low, especially at a high temperature compared to the pure sample. And from the measured thermal conductivity and power factor, the ZT has been calculated. So although the ZT is quite low for this oxide material, there is a systematic change observed for the bismuth free as well as bismuth substituted sample. So this shows that the bismuth substitution is having some strong influence on enhancing the thermoelectric performance of this zinc cobalt oxide materials. And similarly, we have analyzed the thermoelectric characteristics of zinc oxide. Okay, so this is another system like aluminum substituted zinc oxide. So in that the similar procedure has been followed and synthesized by the solution process, and the protocol is almost the same, and the aluminum content has been systematically varied like that, and we have made the sample as a powder as a pellet and subjected to the basic characteristics as well as the thermoelectric analysis. Okay, and look at the X-ray diffraction pattern. So some interesting features has been observed. The first sample is a pure sample. The pure sample shows the Woodside structure of zinc oxide, and when the aluminum content increased in the system, the secondary phase has been obtained, and secondary phase of zinc aluminate has been obtained. This is also a semiconductor phase, and when the aluminum content increased further, the alumina phase also been obtained. Okay, so this kind of three different phases has been obtained in the zinc aluminum oxide, and that is mainly due to the very low solid solubility limit of aluminum in the zinc oxide. Okay, and the substitution of aluminum has been confirmed by systematic shift in the diffraction peaks. And the morphology also changed with respect to the aluminum content from the sheets to the rod-like morphology. And the presence of aluminum has been confirmed by the EDX analysis. And this is the the aluminum content variation in the sample with respect to the variation in the aluminum in the precursor. Okay. Then the electrical characteristics has been measured, and the electrical conductivity has been increased up to 15% of aluminum and drastically decreased. So the up to 15%, the aluminum has been systematically substituted at the zinc site, and due to the heterovalence nature of aluminum, the conductivity has been enhanced, and due to the formation of secondary phase poor conductive alumina, the electrical conductivity has been decreased for the high content sample. Okay, and then the Seebeck coefficient has been measured by using this indigenously fabricated thermoelectric system. So this is a vertical based thermoelectric system where you can place the sample in between the hot end and cold end, and then you can have the thermocouple at the hot end and cold end, and by using that you can measure the temperature difference as well as the thermo EMF, and the same thing can be inserted into the external furnace. There you can measure the the Seebeck coefficient at different temperature. and the Seebeck coefficient has been reasonably improved for the aluminum content with 20% compared to the sample with the low aluminum content. Okay, and then the power factor has been enhanced reasonably for the bismuth aluminum substituted sample, especially at 10%, whereas the power factor is quite low at 20%. That is mainly due to the formation of pore conductive phases, secondary phases. And the zinc cobalt oxide. So instead of aluminum, we have tried with cobalt, and the protocol is almost the same. And look at the pattern. The pattern is quite stable, identical, and up to 20% of cobalt, unlike the aluminum substituted system. So that the cobalt is completely dissolved in the zinc oxide lattice due to high solid solubility limit of cobalt. Okay, and the slight shift has been obtained in this diffraction pattern, which confirms the substitution of cobalt in the zinc oxide lattice. And the morphology is the hexagonal morphology has been observed in the pure sample, and by increasing the cobalt content, the morphology is almost retained, but the size is slightly decreased. And the presence of cobalt in the system has been confirmed by the EDS analysis. Okay, and look at the pattern. This is for a pure zinc oxide. The pattern is there is no cobalt related peak, whereas in the cobalt substituted system, the clear peak has been obtained, so which confirms the incorporation of cobalt in the zinc oxide lattice. Okay, and then once again, the presence of cobalt in the zinc oxide has been confirmed by the XPS. And look at the pattern, the XPS spectrum. So it shows the 2p zinc and oxygen 1s spectra, and this is for the cobalt substituted system. So in addition with the zinc and oxygen, the cobalt peak has been obtained, so which further confirms the presence of cobalt. And then the sample has been subjected for electrical and Seebeck coefficient measurement. The electrical conductivity has been enhanced for the cobalt substituted sample compared to the pure sample, which is mainly due to the heterovalence nature of cobalt in the zinc oxide. Okay, and then the Seebeck coefficient has been measured, which shows there's obvious variation with respect to the cobalt content in the system. So from the measured electrical conductivity and Seebeck coefficient, the power factor has been calculated, and the power factor is quite high for the 20% cobalt substituted sample. So which shows that by properly choosing the dopant with the different valence state, one can tune the electrical characteristics of the material. Thereby, one can enhance the thermoelectric performance of the oxide-based thermoelectric materials. Okay, so this is my summary. So we have prepared a lot of thermoelectric material, especially oxide-based thermoelectric material and semiconductor-based thermoelectric material. So in this particular topic, I've shown some of the results on zinc cobalt oxide and zinc oxide, and systematically varied the heterovalence dopant in the system, and the substitution of dopant is effectively modified the thermoelectric characteristics. So I'd like to acknowledge our funding agencies like DST SERB and ICCIMR and JIMR, Japan. Thank you. Thank you once again for all your patient listening. So if you have any clarifications or doubt, please go ahead.
நீ ஏதாவது கொஸ்டின் கேட்குறீங்களான்னு கேளுங்க. ரவி, நீ சொல்லுங்க, ஏதாவது கொஸ்டின் கேட்குறீங்களா?
Thank you, sir, for enlightening us with your valuable words. Now, people in the gathering can ask any queries if you have.
I have got a fundamental doubt.
Yes, sir.
What exactly the chemical potential means? What are all the parameters or factors on which this chemical potential depends?
The chemical
Influence of chemical potential on the influence of chemical potential on these parameters.
Yes, sir. The chemical potential mainly determined based on the dopant level in the system. So by changing the dopant level, you can tune with the chemical potential of the system. So by tuning the chemical potential, you can play with the electron transport characteristics in the material.
You can tune the chemical potential.
Yeah, by properly choosing the doping material with the multiple valence state.
Dr. Sundar. Huh? Correct. What happened?
Now, I request Dr. S. Ravi to deliver the oath of thanks.
Friends, courtesy demands vote of thanks. These kind of webinars are of much need to overcome this pandemic subtleness. So our head of the department, Dr. S. Pari, and his scholar Satish and Vasuki has taken a great leap in arranging such webinars. Our immense and heartfelt thanks to them. Further, his choice of speakers is highly impressive. Dr. Arivanandhan is one such brilliant choice, sitting somewhere with his skill of explaining complex problems in a simple manner. He was able to keep all the listeners intact and impress them. And thank you, Dr. Arivanandhan, for your exuberant lecture. Thank you so much. Our sincere thanks to all our staff members and participants, and of course, the two personalities on whom we can always rely on for such endeavors. Our respected secretary and beloved principal, they deserve our heartfelt and sincere thanks. Thank you, one and all. Thank you so much. Over to Vasuki. Thank you, Dr. Arivanandhan. Thank you so much.
Thank you for sharing your valuable time with us, sir. And we promise you that we will uh, turn your words into action.
Yes, sir. Thank you very much, sir. Thank you, sir. Thank you, sir. Yes,
Thank you.
sir. Thank
Thank
you.
you.
Thank you, sir.
Thank you.
Bye-bye.